Okay, today we will move to chapter 3, Evaluating Properties. This chapter is very important in determining the correct data for properties like enthalpy, entropy, internal energy, specific volume, any other properties that you need for solving the engineering problem. So please make sure to understand and for following up this chapter. Okay, and I hope you to solve as many problem as possible through this chapter and homework. Okay. Okay. First section we go over first pure substance and phase. What is the pure substance and what is phase? Pure substance and phase. First, let's look at the pure substance. We need to have a definition about pure substance. What is a pure substance? Pure substance is defined as a material with a homogeneous and invariable composition. Okay? So homogeneous property means we have to have the same property at any location, okay, inside one material. Okay? If you pick any position, then they should have same property, okay? Same enthalpy or same internal energy, like that. Okay? Invariable composition means the composition should keep same, okay, as they formed. Okay? So the pure substance is a material with homogeneous and invariable composition. Okay. Of course, the pure substance can have multiple phases, like solid, liquid, and gas. Okay. Those phases are allowable for the pure substance. For example, if we have pure oxygen, okay, and pure nitrogen and pure H2O, okay, so those components can be regarded as a pure substance if they exist with only one single component. Okay, so for example, H2O, if we have a pure H2O in solid ice or liquid water and gas vapor of H2O, pure H2O 100%, then it is regarded as a pure substance. But if we have a mixture together, like nitrogen and H2O, or oxygen and H2O, or integrated composition, then we cannot regard this as those as pure substance. Okay? That is a chemical mixture. Okay? So, for example, air and steam mixture is not a pure substance. Okay. Okay. But we have some exceptional case. The air actually, as you know, has 20% of oxygen and 79% of nitrogen and few argon and other stuff. Okay? But air will be regarded as a pure substance. Okay? But we will have some little error. Okay, so but anyway, in this thermodynamics area, air is regarded as a pure substance. Okay. Okay. And also it can be mixture. Okay, it can be mixture as long as it's homogeneous. Okay. So the mixture can be regarded as a pure substance if it is a homogeneous property. Okay. Okay. Next, phases. We already talked about the definition of phases before. Okay, but I will remind you once again in terms of the structure of molecules. For first, solid has three-dimensional lattice. Okay, so and their distance is very close relative to other liquid or gas. And liquid, yeah, we have some movable and rotating freely, but their molecules are quite close. Okay, close. So it is moving and rotating freely, okay? And they are quite close each other. Okay? How about gas phase? Gas phase, yeah, the molecules in gas are very apart, far apart. Okay, molecules far apart. Okay. Okay. Let's look at the phase changing. At section 2, let's look at phase changing. Okay. Let's suppose to have one skillet. Okay. In the skillet we have water, liquid water. Okay. And atmospheric surrounding the pressure is atmospheric pressure. Okay. Is 1 bar or 100 kilopascal. Okay. And we will add some heat to evaporate this liquid water. Then we will have some evaporation to air. Okay. Evaporation of liquid water to air. So the water vapor will be leaked to the air, so that we will have some mixture because it is open. Okay? So we will have some mixture with moisture vapor plus air. Okay? So it is regarded as a mixture, but it is not pure substance. Okay? It is not pure substance. Not pure substance. Okay? So we need to have a closed system to talk about the pure substance. Okay, let's take a look at the pure substance in the closed system, and so that we can have only pure water vapor. Okay. First, let's figure out from the ambient temperature water, liquid water, and we have of course 100 kilopascal ambient pressure. Okay, 100 pascal. And we will close with some piston. Okay, so that we can have a closed system with water. Okay. First, we have water at liquid phase, and temperature is 20 degrees C. Okay, 20 degrees C, which is ambient temperature. At this the pressure, ambient pressure, of course, water is existing at liquid phase, right? Okay. And we will start heat transfer to the water. Okay. We will start heat. We will add heat to the cylinder system. Q is added to the system. Then the water is still liquid because it is under saturation temperature of this pressure. Temperature is increasing, then 20 degrees C, right? as we increase this temperature of water, liquid water, we have slightly increased volume of liquid water, right? So volume is increased this much, okay? And we still keep heating this liquid water, okay, with increased volume. This is a piston, so that we can have a closed system, and we will have water heating until we have a saturated temperature at 99.62 degrees C. Okay? The saturation temperature that we start vaporization under ambient pressure is 99.62 degrees C. I will let you know how to find out that saturation temperature later, but at this time I just inform you the water saturation temperature under this pressure is 99.62 degrees C. Okay? We still have heat addition to the system. Okay? And once we reach this temperature, saturation temperature of this pressure, then we begin to phase transition from liquid to vapor. Okay? Okay. We keep going on heating to the piston, and finally we will have the vapor two phase. Okay? This is saturated liquid. Okay? So it is initial. As soon as we reach this temperature, we call it saturated liquid. We have still only the liquid phase. But if we keep heating this saturated liquid more, then we will have the evaporation to vapor. So we will have a mixture of vapor and liquid, because we have evaporation from this saturated liquid. Okay? So we call it saturated vapor, okay, and saturated liquid. But we have still same temperature. Temperature is 99.60 degrees C. Even though we keep adding this heat to the system, we still have the same temperature until we finish all the phase transition from liquid to vapor. Okay. Okay. We keep heating this, and we will increase the volume of a mixture of liquid and vapor until we have all fully saturated vapor. Okay, saturated vapor. And we still have the same temperature. Temperature is 99.62 degrees C. And we still have a heat addition to the system. Okay. And volume is increased. And so we will have a fully vapor, saturated vapor here. And we have the same temperature. So from the beginning of saturation, phase change, to the end of phase change as a saturation vapor, we will have a isothermal condition, which is the same temperature, okay, as 99.62 degrees C. Okay. There is no the sensible heat change, sensible temperature increase. Okay, okay, next. If we keep add heat to the system, okay, finally we can have of course we will have a larger volume than before, but the vapor will be superheated vapor, and temperature will be increased finally. Okay, so that temperature will be higher than 99.62 degrees C. Okay, so let's number this state, number 1, number 2, 3, 4, 5, 6. Okay. We have heat addition from 1 to 6. We begin from the liquid water at 20 degrees C, and once we start heat addition, we will have temperature increase from 20 degrees C until we have saturated liquid. Okay. So we have a sensible heat transfer, okay, because we have a temperature increasing. And once we reach the saturation temperature of this corresponding this pressure, ambient pressure, then we start the phase change from liquid to vapor. And in the beginning, we call it this state, the fully saturated liquid, as the saturated liquid, okay, and then we will have a two phase with saturated vapor and saturated liquid, okay, and we still have the same temperature as the saturation temperature, 99.62 degrees C. And once we reach full saturated vapor, there is no liquid here. Okay? So we will have a full phase transition from saturated liquid to saturated vapor with the same temperature. Okay? So this is called the latent heat transfer. And then once we have a fully saturated vapor, then we can get the superheated vapor, okay, which is higher than 99.62 degrees C. Okay? Okay. So from the beginning of this phase transition and to the end, we will have a constant temperature. Okay. And this is also isothermal condition. Okay. And let's look at this phase transition phenomena in terms of temperature and vapor graph like this. Okay, we start from the 20 degrees C. Okay. Unit will be degrees C. Okay. Volume is cubic meter per kilogram. Okay. And then the temperature increase. Temperature is increasing from 20 to 99.62 degrees C, and volume is also increased, right? Volume is continuously increased, and temperature will be 99.62 degrees C, which is the saturation temperature of this ambient pressure. Okay, and during once we start the phase transition, and we will have a constant temperature until we have a fully saturated vapor. And once we have a full saturated vapor, then we can have a temperature increase to be superheated vapor. This. Okay. All right, and let's match those numbering to this graph. First, our beginning point will be number 1 at liquid water at 20 degrees C. And in the meantime, we have temperature increase like here. We're supposed to have number 2 here, the middle of those the temperature point. Okay, and number 3, saturated liquid is here. Okay, because we began just the phase transition from here. Number 3 is the starting point of this isothermal condition. And in the middle, we will have a mixture between saturated vapor and liquid. Okay. We have number 4 status. And number 5 state with saturated vapor will be here. Okay. Because number 5, full saturated vapor without any liquid is the end of isothermal condition. Okay. Then we will have a superheated vapor with increased temperature than this saturated. Okay. So 99.62 is the isothermal condition, as well as saturation temperature of 100 kilopascal. Okay. 100 kilopascal is the atmospheric pressure, right? Okay. And let's look at the heat transfer. Heat transfer accompanying with a sensible temperature change is called sensible heat transfer. Okay. So we have here from 1 to 3, we call it sensible heat transfer, which is sensible heat transfer. Okay. And from 3 to 5 until we finish all the phase transition, we call it latent heat transfer. Okay. And once we finish latent heat transfer, then we start again sensible heat transfer to be superheated. Okay. All right. And we call this state, okay, the liquid phase under the saturation temperature as compressed liquid water. Compressed or subcooled liquid water. Okay. Of course, the number 2 is the same state, right? Compressed or subcooled liquid water. Number 3 is called saturated liquid. Okay. We have full liquid here at number 3. Okay. And number 4 is a saturated liquid plus vapor mixture. Okay, we still have the same temperature. Okay. We have mixture between liquid and vapor. And number 3, we have only fully liquid. There is no vapor. So we have here single phase. But here, once we started this phase transition, we will have 2 phase with liquid and vapor, right? 2 phase. Once we finish the whole phase transition process, then we will have again single phase as a saturated vapor. Okay. Then we have continuous heating. Then we have still single phase as a superheated vapor. Okay, superheated vapor. Of course, number 1 and number 2 is a single phase as a liquid phase. Okay, so we have a single phase as a liquid water, like compressed or subcooled liquid water. Then we have the saturated liquid and vapor mixture and saturated vapor. Okay, as a 2-phase flow, 2-phase, and then if we have continuous heating, then we can get superheated vapor as a single phase. So single phase, 2-phase, and single phase. And we have a sensible heat transfer, latent heat transfer, and then sensible heat transfer. Okay? So to be for water to be a superheated vapor, we need to experience those kind of heat input to the system. Okay. Okay. And since we have no resistant force to the piston through number 1 to 6, we have an isobaric process. Okay. So this line is an isobaric line as a P equal 100 kilopascal or 1 bar. Okay. So let's make the feature of this diagram. We have to have isobaric process, okay, through 1 to 6. Okay, 1 to 6, so we will have isobaric process. Of course, if we put something here, okay, so that we can have the same volume. Okay, if you have any resistant force, okay, to make isocoric constant volume process, then it is not isobaric process. But we will let this piston assembly free, okay, so that they can increase the volume. Okay. So it is regarded as an isobaric process. And number 2, volume is increased, right, through to 1 to 6. Okay. we will have a continuous increase of volume. Volume increases. Okay, and because we have the molecules moving more, okay, from the liquid phase to a vapor phase. Okay. The distance between molecules of water is increased, okay, from liquid to vapor. Okay. How about temperature? Yes, temperature is also increases, okay, from 20 to saturated temperature, and from saturated temperature to superheated temperature, right? Temperature is increased. What else? Yeah, please look at the saturation temperature. We have a saturation temperature. This saturation temperature is 99.62 degrees C at this atmospheric pressure. Okay? So saturation temperature is proportional to pressure of the system. So if we have a higher pressure in the system, okay, then we will have increased the higher saturation temperature. In other words, if we have lower operating pressure than this atmospheric, like 50 kilopascal or 1 kilopascal, then we will have a lower saturation temperature of water. Okay? Okay, that's it. Okay, next let's look at the comparison between the liquid and vapor. Usually, typically, the liquid is dense than vapor, right? That means the density of liquid, and that's the density of gas. Okay, usually density of liquid is larger than density of gas, right? In this section and other the table, we will use the liquid will be symbolized as F, which is fluid, okay? And gas will be symbolized with G. Okay, so we can rewrite this comparison as density of F, which is larger than density of G of that pure material. Okay, and you know the specific volume is inverse number of density, right? So if you convert this density to specific volume, then we will have a specific volume of liquid and specific volume of vapor, gas phase. Okay. Then since we have an inverse number of each density, then we will have the inverse relationship than density, right? So because the specific volume is the inverse number of density, usually we have a larger distance between molecules in gas phase than liquid phase. So specific volume of gas is larger than the specific volume of liquid, right? In other words, the density of fluid liquid is larger than the density of gas phase. Okay. Okay. Next, let's look at the important the property quality. Okay. Quality is symbolized with X. The quality is defined as the ratio of the mass of vapor to the total mixture mass. Okay? Mass. So the ratio of the mass of the vapor to the total mixture mass. Okay. So let's look at the closed system with a mixture. Let's have the mass of vapor mg and mass of fluid, liquid. Okay? So if you calculate the total mass of this mixture will be mg plus mf. Okay? Mass of vapor and mass of liquid, right? And we can determine the quality of X of this mixture as mass of G, mg over m tot. Okay? M tot again, m tot is mg plus mf. Okay? Okay, for example, if we have zero quality, that means mg, okay, mg is equal to 0. That means we will have all liquid, because there is no mass of vapor inside the system. That means we have full liquid in this system. And also, if we have unity of quality, if we have x equal 1, that means mg is equal to m tot, right? mg should be the same as m tot. That means we will have all vapor, gas phase. Okay. How about x equal 0.5? If x is larger than 0 and less than 1, like 0.5, then we have mg is 0.5 times m tot. Okay. So the half percentage in terms of mass of total mass is vapor, right? So half mass is vapor. Another half mass will be liquid. Okay, in terms of mass. So the quality X is a percentage of mass of vapor to the total mixture. Okay. So X varies from 0 to 1. Okay. So since we talk about mixture, that means we can define only X at saturated phase, saturated state. So, for example, if we have X equal 1, X equal 0, and then we have all liquid, right? That means if X equal 0, okay, at saturated state, then we will have saturated liquid. Okay. If X equal 1 at saturated state, then we will have saturated vapor. Okay. If X is larger than 0 or less than 1, okay, like 0.5, 0.3, 0.7, okay, that state is called saturated liquid plus vapor mixture. So we have two phases. Okay. Okay, next let's draw the TV temperature and specific volume diagram for the water vapor and or any pure substance. I told you the saturation temperature is proportional to saturation pressure. Right? Saturation temperature is proportional to saturation pressure. It is determined by the test experimentation of a scientist. And let's look at the TV diagram here, temperature and specific volume. Temperature should be unit in degree C, and volume, specific volume is in cubic meter per kilogram. And for example, if we have the 1 bar, like atmospheric pressure, we will experience like this kind of the temperature profile. Okay? So the temperature, there is a proportional relationship between temperature and specific volume. Okay, but once we reach the saturation temperature of corresponding the saturation pressure, then we will have isothermal condition. Okay, so we have a sensible temperature increase with a specific volume, and if we add more heat, we will experience the isothermal temperature condition. And then we have superheating with the sensible heat. Okay? And if we have a higher pressure, then we will have a higher saturation temperature, like this. Okay? And if we have lower pressure, then we will have a lower saturation temperature. Okay? Okay. So if we connect, we have here saturation liquid point, right? And we have here saturated vapor point. Okay? And here in the middle we will have a mixture with saturated liquid and vapor, right? If you connect all saturated liquid line, okay, then we can get this curve. And if you connect all saturated vapor line, then we will have a line this. So this line at center, at the end of this curve peak, we have a critical point. Okay, critical point. Okay. At critical point, we don't need any more latent heat for phase transition. We have direct the phase transition from liquid to base without any latent heat. We need latent heat for the under the critical point. Okay? And as the pressure is going down, we need a larger latent heat, right? Okay. Yeah. And from this critical point to the left, the end of the left line, this line, okay, we connected all the saturated liquid line, right? We have here saturated liquid point. Okay? The line is called saturated liquid line. Okay? And we connected all the saturated vapor point. Okay? This point is saturated vapor. Okay? We connected all the saturated vapor line from critical point to the end. This line is called saturated vapor line. Okay? So we need to draw this saturated liquid and vapor line with the critical point. Critical point of water is known as TC is the critical temperature of water vapor is 374.14 degrees C. Okay. And pressure, we have to have a pressure, okay, passing this critical point, which is critical pressure. Critical pressure is 22.09 megapascal. If you convert this to bar, we will have 220 bar. 220 bar as a critical pressure. Okay. You can find the critical information about critical temperature and pressure at table A-1. Okay. We have a list of pure substance here, and if you look at water at the bottom, you have a critical temperature and pressure in Kelvin. If you convert this to degrees C, of course, we will have 374.14 degrees C, and the critical pressure in bar is 220.9. Okay? For example, if you look at other information like oxygen, we have a critical temperature information and pressure here. Okay? So you can find the critical information from table A-1. Okay. So, for example, let's draw the typical saturation pressure and saturation temperature. Let's suppose to have here pressure equal 1 megapascal, which is 10 bar. Okay? And let's make this pressure as 0.1 megapascal, which is 1 bar. Okay? And this can be, the pressure of this line will be 10 megapascal, which is 100 bar. Okay? Through those each pressure line, we will have a isobaric process, right? Because it follows up with one single curve with a constant pressure curve. Okay? Each curve means okay, pressure, the isobaric process. Okay? And if we have a center line, okay, through this critical point, at left side we will have a liquid phase. At right side of this line, this dashed line, and right side of a saturated vapor line, we will have a vapor. Okay, and between saturated liquid and saturated vapor line, we will have mixture with liquid and vapor. Okay, so we will have liquid and vapor and mixture of liquid and vapor inside this, the saturated liquid line and saturated vapor line. Okay, and for the phase, for the liquid phase, the left side of saturated liquid line, we call it, this phase is called the compressed liquid or subcooled liquid. Okay. For right side of saturated vapor line, which is higher than each of the saturation temperature, this side is called superheated vapor. Okay, so according to this the diagram, vapor, the specific volume of the pure substance has increased with temperature, right? As we have a temperature increased, the volume is the specific volume is increased. Okay? We have overall the proportional relationship between temperature and specific volume. Okay, so the superheated in the one isobaric process, the specific volume of superheated vapor is larger than specific volume of compressed liquid, right? Okay. And we can also draw the corresponding saturation temperature of each pressure, right? For example, the saturation temperature of 1 bar is known as 99.62 degrees C, right? Okay, and can we find the saturation temperature of the 10 bar? Okay, yes. If you go to a table A3 is the coming with first the pressure, okay, and table A2 is starting from the temperature. Okay, they have same table for the saturated water, but we need to look at first the pressure table because we have only known variable here, the pressure. So let's look at 10 bar at table A3, page 893, 10 bar, and we have a saturation temperature corresponding to this 10 bar is 179.9 degrees C. So the saturation temperature of 10 bar is here 179.9 degrees C. Okay, how about 100 bar? Yes, the saturation temperature of 100 bar is 311.1. 311.1 degrees C. Okay. Okay. So by marking the temperature and pressure isobaric line, okay, and saturated liquid line and vapor line and critical point, okay, we can accomplish the TV, the temperature and specific volume diagram for the pure substance like water. Okay. And please look at this. If any state of material, the pure substance like water, has a temperature higher than the saturation temperature, like this point, okay, then the state of this point will be superheated, right? And also, if we have any state at exactly same temperature as the saturation temperature, like this, okay, that state will be defined as saturated. Okay. It can be saturated liquid and vapor mixture, or it can be saturated liquid, or it can be saturated vapor. So, okay. So in this range, we will have X quality from 0 to 1, right? And also, if we have, for example, if we have temperature of a specific state is lower than the saturation temperature of the corresponding pressure, like this point, okay, this point is called as compressed or subcooled liquid. Okay, so the temperature of material and pressure with two property, intensive property, we can define the state if it is superheated or saturated or subcooled or compressed liquid. Okay, so again, if the temperature of material is higher than saturation temperature of corresponding pressure, okay, like this, then we can define this state as superheated, right? Okay, obviously. And if the temperature is exactly same as the saturation temperature, then we can call it that state is in saturated. And if the temperature is less than saturation temperature, of course, the state is defined as the liquid phase, okay, the compressed or subcooled liquid, okay. And for the critical point information, like if we need to have the specific volume at critical point, we can go to the table at A2 or 3. A2 or 3. If you go to the last row of the table A2, we have a critical point 374.14 degrees C at pressure 220.9 bar. Okay. If you go to here, the specific volume, okay, we have same, they should be same, right? Because we have no the VF and VG. So saturated liquid and saturated vapor should have the exactly same value on the specific volume. The specific volume is 0.033155. Okay, so this point is VC, right? VC is 0.003155 cubic meter per kilogram. Okay, then we can finish the drawing of the TV diagram of water vapor. Okay, next we will draw pressure and specific volume diagram. Before doing that, please remind the Boyle's law in physics and Charles' law. Boyle's law has the Boyle's law is defining the relationship between pressure and specific volume, right? So Boyle's law has a relationship between pressure and volume. Okay, and they are inverse proportional relationship, right? For the gas. So if we increase the pressure, volume will be reduced. Okay? And Charles' law says temperature and volume. Okay? So if we increase the temperature, volume will be increased. So they are the relationship between temperature and volume is proportional each other. Okay, think about that. So we will have a kind of inverse proportional relationship between pressure and volume. Okay, like this. For pure substance that has the phase transition between liquid and vapor phase. Okay, so we have pressure and vapor. Pressure will be y-axis in let's make that as megapascal. Okay, it's like different the unit. Okay, and specific volume will be cubic meter per kilogram. Okay, and as you know, we will under the critical point we should have the latent heat in isothermal condition, right? So we will have to have the mixture with the liquid and vapor, right? So like this, and but the overall trend between pressure and volume should be inverse proportional. This, okay, this, and if we have the lower pressure, of course we will have a lower saturation temperature, right? Like this, okay, and if you connect all the saturated liquid line, then we will have this shape and this shape. Okay, and we will have here the critical point. Okay? Critical point of water at pressure will be 22.09 megapascal. Okay, and specific volume we already found that, right? The critical property. The VC will be 0.003155, okay, cubic meter per kilogram. Okay, and if you draw the critical line, we have no the latent heat, right? So we will have just the linear like the curve. Okay, okay, and we have the for the TV diagram we had the isobaric pressure line, okay, the constant pressure line. But for the PV diagram, we will have an isothermal line. Okay. For example, for this line, if we have a saturation pressure for this, the horizontal curve, if we have 0.1 megapascal, which is equivalent as 1 bar, right? Ambient pressure. Okay. Then the isothermal curve passing this saturation pressure will be what? Saturation temperature of corresponding this pressure, which is 99.63 degrees C. Okay. So through this line, we will have isothermal process. Okay, and this point, we will call this point as a saturated liquid point. Okay, and this point will be saturated vapor. Okay, in between saturated liquid and vapor, we will have a saturated liquid and vapor mixture. Okay, and at the left side of saturated liquid line, we will have over the liquid phase, and at the right side of saturated vapor line, we will have vapor phase. Okay. So, and we can also mark one more the pressure, the isothermal curve here. For example, if we have a saturation pressure of this horizontal line is like 10 bar, like 1 megapascal, okay, 1 megapascal. The corresponding saturation temperature of 1 megapascal will be 179.9 degrees C. Okay, so we will have isothermal curve with 170.9 degrees C. All the temperature following this curve will have the same temperature as this one. Okay, and as we have a higher saturation pressure, we will have increased saturation temperature. If we have lower saturation pressure, we will have lower the saturation temperature. Okay. Okay. And also, if we have the higher pressure than saturation pressure of certain point like this, okay, then this is a liquid, right? Okay, this state is defined as a liquid phase. And if the pressure of a specific point is lower than saturation pressure, like this point, yes, this point is defined, state is defined as a compressed or subcooled liquid, right? Okay. And also, if any state is in exactly same pressure as saturation pressure, like this point, okay, this state is defined as a saturated liquid and vapor mixture. Okay. Okay. And we will have reduced. We will require reduced latent heat as going higher saturation pressure. Okay. And then this is minimized as 0 at critical point. So we don't require any latent heat for phase transition from liquid to vapor. Okay, so this is about the PV diagram for water vapor. Okay, we drew the curve for the temperature and specific volume for water, as well as pressure and specific volume curve for the water, same material. Okay. Now we will look at one more curve, combining the pressure and temperature, okay, for water. Y-axis will be the pressure in kilopascal. X-axis will be temperature in degrees C. Okay. Now there is a point which is called the triple point, which means the coexisting point of three phases: solid, liquid, and vapor. Okay? That point will be center of this drawing, and the triple point is known as the 0.01 degrees C, almost 0 degrees C. Okay? And the pressure of triple point is 0.6113, okay, kilopascal. At this triple point, we call it triple point, we have coexisting phase with including solid, ice, and water, liquid, and vapor. Okay. From this triple point to the origin, we will have a sublimation curve. Okay, sublimation means we have a phase transition directly from solid to vapor and vapor to solid. And from the triple point to the left, we will have a fusion line between solid and liquid. Okay, and this is a fusion line. Okay. And from the triple point to the right, we will have a vaporization curve. Vaporization line, okay, and it is end at critical point. Okay. So between the fusion line and sublimation, we will have a solid phase, okay, and between fusion and vaporization line, we will have a liquid, compressed liquid. Okay. Under vaporization and sublimation, we will have a vapor, okay, gas. So this, for example, if we have the temperature increase at isobaric process like this under the triple point process line this, okay, we will have a sublimation phase transition from directly from solid ice to vapor, okay, or sublimation from the vapor to ice, okay, if we increase the temperature at constant pressure. Okay. Let's look at the fusion line. For example, if we have a constant the pressure process, and if we have increased temperature from this point to here at isobaric process, then we will have a phase transition from solid to liquid, like ice will be melted to liquid. Again, if we have the inverse direction, okay, then we will have melting from liquid to solid, okay, the crystallization from liquid to solid, okay. And for example, let's look at this another constant pressure line. If we have temperature increase with isobaric process, okay, we have constant process in this line, okay, because y-axis is pressure. If we increase temperature at this through the vaporization line, of course we will have boiling, like evaporation from liquid to liquid to vapor. And if we reduce temperature, if we cool down at isobaric process from this point to here, yes, we will have a liquid vapor to liquid phase transition, which is called condensation. Okay, so this way, solid to liquid, we have melting. Okay, from liquid to solid, we have a crystallization. From liquid to vapor, we have a boiling or evaporation. From vapor to liquid, we will have a condensation. Okay, and as you know, critical point can be marked here. Okay, you know, the critical pressure of water is in kilopascal to 22,090 kilopascal, right? It was 22.09 megapascal, right? But if you express in kilopascal, yeah, we need to multiply 1,000 to that, right? And critical temperature will be 374.14 USC. Then we can accomplish the phase diagram for water. Okay. And also, you can also have another example like this. If we have an isothermal line like this, okay, and through this isothermal process, if you increase the pressure from here to here, okay, yes, we will have a sublimation from vapor to solid, right? If you increase the pressure at same temperature, and if you decrease the pressure from this point to here at isothermal process, yes, we will have a sublimation phase transition from solid to vapor. Okay. Okay, it's it is happened at under the triple point. Above the triple point, if we have an isothermal process like this, because we have x-axis. Okay? Okay? The initial point and final point of temperature is the same. Okay? So in isothermal process, if you increase pressure from solid to liquid this way, yeah, we will have phase transition from solid to liquid. And if you decrease pressure this way, okay, and we will have a phase transition from liquid to solid. Okay. Now let's look at the vapor. If we have another example for the isothermal process between liquid and vapor, if you increase pressure at isothermal process, okay, through this vaporization line, yes, we will have a phase transition from vapor to liquid. Okay. At isothermal condition, if you increase pressure, so we will compress the molecular distance to very close, right? So we can transition to the liquid. But if you release the pressure, if you lower the pressure at isothermal process like this, yeah, then we will have a phase transition from liquid to vapor evaporation. Okay, so you can understand right that way.